Hello everyone. I welcome all of you. Uh, in the previous lesson, we derived expression for the drift velocity. So in this lesson, we will try to understand how a drift velocity depends on various physical quantities. So from the previous lesson, Vd is equals to E by m into tau. So this E is the charge of the electron. This is capital E is the electric field inside the conductor. M is the mass of the charge carrier, that is the mass of the electron, and tau is the relaxation time. So if you look at the equation, this the charge of the electron and the mass of the electrons are constant. So increasing the value of E increases the value of Vd, or we say that the drift velocity is directly proportional to electric field. If I replace E, electric field, by V divided by L, so we can see here drift velocity is directly proportional to the potential difference across the conductor, and the drift velocity is inversely proportional to the length of the conductor. So before moving forward, let me explain the term directly proportional and inversely proportional. So I have summarized it here. Vd is directly proportional to E. It means increasing E increases Vd, or decreasing E decreases Vd. So this type of relationship is known as directly proportional. So here, increasing the value of L decreases Vd, or decreasing L increases Vd. So this type of relation is called inversely proportional relation. Next is the relationship between drift velocity and relaxation time. So for this, we need to understand the relationship between relaxation time and temperature. So if we see here, if we increase the temperature of this conductor, then the collision frequency of this electron increases. Now, since relaxation time is the average time interval between two consecutive collision, so increasing temperature, uh, the relaxation time decreases. That means these electrons will collide frequently, and therefore the average time interval between two consecutive collision decreases. So hence, a relaxation time is inversely proportional to temperature, or drift velocity is inversely proportional to temperature. Now next is the relationship between the cross-sectional area of a conductor and the drift velocity. For this, let me go to the next slide, this one. So I is equals to NEAVD. So Vd is the drift velocity, A is the area of cross-section, E is the charge of the electron, and N is the density of free electrons inside the conductor. So this is the relationship between current and the drift velocity. So by looking at this equation, it seems Vd is inversely proportional to the area of cross section. But we are missing one very important point here. So when we change the area of a conductor, the area of cross section of a conductor, the value of the current also changes. So this we can understand using Ohm's law. So I is equal to V by R. This is Ohm's law. If I write R in terms of the length and area of cross section of a conductor, so we are at this equation. So here we can see if we increase the value, if we increase A, the area of cross section, so I also increases. So now moving here again, so Vd, if we increase A, then I also increases. If we decrease A, I also decreases. So because of this, the increment in I cancels the increment in A. Therefore, Vd is, or the drift velocity is, independent of the area of cross section of a conductor, provided the length remains constant. To summarize the whole lesson, drift velocity for a conductor is directly proportional to electric field, or the potential difference across the conductor. Uh, Relaxation time is inversely proportional to temperature, and drift velocity is inversely proportional to temperature.